Welcome back. This is Week 2's first video. It'll be about limits at infinity. Okay, we'll start with the random animation. Okay, so we want to talk about the idea of a limit at infinity, meaning that we look at a function and the function is defined on an interval all the way to the right positive infinity. And we want to know what's the limit as x gets bigger and bigger, approaching infinity. What happened to the function? If that limit of that function approaches a number L, then we want to kind of explain geometrically or graphically what does that mean for a function to approach a particular number L. So there's really three ways that this can happen. So here's the y value being equal to L. And then we look at a function. And notice that this function has this property that as I approach infinity on the positive side, on the right side, as x approaches infinity, the functions get closer and closer to the value L. Here's another example. This one, it kind of go down for a little bit, but eventually, as x approaches infinity, it gets closer and closer to L as well. Here's another one. Again, this one will kind of go up and down a little bit, but eventually, it's going to approach infinity. And so that's basically how you want to think about this, is the limit as x approaches infinity of f of x is L if eventually, right, as x gets bigger and bigger, the function approaches a horizontal line. So this is also known as the horizontal asymptote. Okay, so that's basically how you want to understand that definition. But now, here's the other side of that, is that what if x approaches negative infinity? Right, so this is similar, it's just going to infinity towards the left side of the graph. And so what happened as x approaches negative infinity, if that limit is L, then this is basically how you want to visualize it. So again, here's the line y is L, and I'm going to take a point, and I'm going to approach negative infinity. And notice that the function is just getting closer and closer to the y value L. Same thing here. Again, as x approaches in negative infinity, the function is approaching the horizontal line y is L. Now, it's possible that a curve will have not just one horizontal asymptote, as we saw in those previous examples, but maybe two horizontal asymptotes. In fact, 2 is the maximum, right? You can only approach one horizontal asymptote on going to infinity. You can only approach another asymptote going towards negative infinity. So you can only have at most 2 horizontal asymptotes. So here's an example of that. The inverse tangent has this property that if I go towards the right, the positive infinity, the function is approaching pi over 2. And then if I approach negative infinity, the function is approaching negative pi over 2. So there it is on the bottom here. As x approaches negative infinity, the inverse tangent function approaches negative pi over 2. And x approaches positive infinity, the function inverse tangent approaches positive pi over 2. And so that's our formal. This is our formal definition, which we mentioned earlier. Is that this line, this horizontal line y is L, is a horizontal asymptote of the function f of x. If either x approaches infinity, the limit approaches L, or the limit as x approaches negative infinity, the function approaches L. So either you approach L going to positive infinity or negative infinity. In either of these cases, we say that line y is L is a horizontal asymptote. And so in the early case of the inverse tangent, we saw that we have two horizontal asymptote, right? One of them is pi over 2, y is pi over 2. This is a horizontal asymptote. The other one is y is negative pi over 2. Okay, let me go back to the slides now. So we've covered this graphically with Manem. And then here's another example. Here's example 1. So this is where you kind of bring in everything from last week material. Last week we talked about infinite limits. And then today we talked about limits at infinity. And so these two terms are confusing, so I want to clarify this with this example. Again, combining last week vertical asymptote we talked about, and then today's horizontal asymptote. So let's look at this picture, right? So notice that as x approach 2 from the left, here's this limit. So if you look at my mouse, as x approaches 2 from the left, my function is approaching negative infinity. So this is notice this is a vertical asymptote. Again, not horizontal. This is a vertical asymptote. So again, as x approaches 2 from the left, the function is going towards negative infinity. And then as x approaches 2 from the right, again, following my mouse, if I approach 2 from the right, my function is approaching positive infinity. So these are, in this case, right, we have a vertical asymptote when x is 2. Right, so this is infinite limit. This is what we covered last week when we talk about vertical asymptote. So that's infinite limits. Today we talked about limits at infinity, meaning that I'm going to go towards infinity, either positive infinity or negative infinity, and we want to know what is the limit as I do so. So that's today's lecture, which is about horizontal asymptotes. So now let's try it. As x approaches infinity, so again, follow my mouse, as x approaches infinity, what happened to my function? Well, first it kind of goes down and then goes back up, but eventually it approaches a horizontal line, right? As I keep going, it's going to approach this horizontal line, and that line is the line y is 4. So the number 4 here is a horizontal asymptote. The line y is 4 is a horizontal asymptote as x approaches infinity. On the other end of that, what if x approaches negative infinity? Again, the function kind of does something here. It goes down. Eventually, it approaches y is 2, this horizontal line, this horizontal asymptote, y is 2. So that's this side, y, as x approaches negative infinity, the function approaches 2. So we have two different horizontal asymptotes. One that y is 4 above here, and one at y is 2. So those two lines are the two horizontal asymptotes. So again, this is today's work, which is limits at infinity. So this right here, again, my mouse is showing this expression referred to horizontal asymptote. This one referred to vertical asymptotes. Here's another example. The function, the hyperbola y is 1 over x. Notice we have really a bunch of asymptotes. We have a horizontal asymptote that's y is 0. As x approaches infinity, the function approaches 0. In fact, as x approaches negative infinity, we also have the same horizontal asymptote. The y is 0. Notice we also have a vertical asymptote. As x approaches 0 from the right, we have an infinite limit, positive infinity. As x approaches 0 from the left, we have negative infinity. So we have both horizontal and vertical asymptotes. And then here's kind of one more theorem. Turns out that if we have a rational expression like this, 1 over some power of x, where the power r here is positive, it turns out that when x approaches infinity, this term will get so big that eventually this limit will be 0. So this is true for all positive r, and so this limit is always going to be 0. So for example, let's talk about this limit. What is the limit as x approaches infinity of this expression? So that the trick for this is that we notice that when x goes to infinity, the top term here will get really, really big. Right? The minus 2 here doesn't really matter too much. then minus x here doesn't matter too much either, because when x is so big, x squared is going to be a lot bigger than x. It's going to be a lot bigger than a 2. So really, the top term here, that's the only term that matters, 3x squared. And in the bottom, same thing, when x approaches infinity, this 1 doesn't matter too much. Even the 4x doesn't matter. It's the 5x squared that will be dominating. So after a while, right, these things will kind of be so small, the only two terms that matter is really the top, the dominating term. So the one that has the highest power, in this case, is the 2. So we want to know what happened when x gets really, really big. What happened to this function? Right? What happened to this whole expression? One trick is to kind of divide by the highest power. Again, the highest power is x squared. So I divide everything on top and everything at the bottom by x squared, the highest power. If I do that, I can simplify. So here, 3x squared divided by x squared, that's just 3. Negative x over x squared, if you simplify it, it's negative 1 over x. And negative 2 over x squared is just negative 2 over x squared. Same thing at the bottom. Divide everything by x squared. So basically the x squared get canceled out. And then these other terms, right, have an x, some power of x at the bottom. Now this limit is the same as the original limit. So, but this limit is easier because from this previous theorem, we says that whenever you have an x at the bottom with any power, when x approaches infinity, this will go to 0. By the same result here, this will also go to 0, right? When x gets really big, the bottom is so big, 2 divided by something really big will go to 0. Same thing for this term and this term. When x goes to infinity, all these 4 terms go to 0. So everything goes to 0. So the only thing that's left is the 3 and the 5. As x approaches infinity, the 3 and the 5 stays there. They don't change. And so this whole limit is 3 over 5. And that's the horizontal asymptote. And so this means that as x approaches infinity, this limit goes to 3 over 5. Therefore, this is the horizontal asymptote. And we notice that that really the key here is that if the powers are the same, this limit will always give you the coefficient in front of the highest power. This is always going to be true. And so here's the graph of that function. Notice that x approaches infinity. Notice that it gets closer and closer to 0.6, which is 3 over 5. So that's exactly what we found, right? This 3 over 5, or 0.6, that's exactly the horizontal asymptote. You can check that as x approaches negative infinity, you can do the same calculation and find out it's the same horizontal asymptote on the other side. So we only have one horizontal asymptote in this case. And then here's the last thing we'll talk about. So this trick is good to be, you want to memorize this trick. Again, if the power on top and bottom is the same, then the limit as x approaches infinity is just the coefficient of the highest power. Right? Everything kind of goes away, and this function is approximately this function because everything else is so small when x is really, really big. So this limit is 3 over 5. Now, if the power on top, the highest power on top is smaller than the bottom, then this limit will actually go to 0 because as x gets really, really big, the x squared is so small compared to x cubed that eventually, it's just essentially an x at the bottom, right? If you look at this, x cubed is so much bigger than x squared. How much bigger? Well, by a factor of x. So really, as x approaches infinity, this limit is the same thing as this limit. When x is really, really big, this is essentially would be 0. So that's the second case, right? Again, if powers are the same, it's the coefficient in front, 3 over 5. If the power on top is smaller, this limit is always 0. And lastly, if the power on top is well, actually, this is another same case, actually, as the first case. If the powers are the same, and then you have 2 over 3 here. In fact, that's a little bit of a typo here. Technically, I actually want this power to be smaller. Actually, I want this power to be bigger, and that's what this talks about. So I'll change the slide later. If the numerator is bigger than the denominator, that's the case I want. Then this limit would be infinity, right? Because the power on top would be so big that it will go to infinity. Sorry about that typo. I'll fix that in the slides. Okay, so again, just a quick recap. Sorry again for the typo. Is again, if the powers on top is the same, is the coefficient. If the power on top is smaller, 0. If the power on top is bigger, say this was a 6. If this was a 6, then this limit would be infinity. Again, it could be positive, negative, infinity, depends on the numbers in front. If the number is positive, then and this power is bigger than the bottom, it'll be positive infinity. If the number here is if this quotient is negative, and the power on top is bigger than the bottom, say this is a 6, then this would be negative infinity. Okay, that's it for this first video.